Welcome. Let us look at this chemistry practical, the year 2021, but this is the April 2021, meaning it was the exam for 2020. These are the students who were supposed to do an exam in the year 2020. So let us go in and see what they were provided with. You are provided with 5.3 grams solid A, sodium carbonate, solution B, hydrochloric acid. You are required to determine the molar heat of the solution of solid A, concentration of the hydrochloric acid, solution B. Procedure 1. Using a purette, place 30 centimeters cube of distilled water in 100 milliliter plastic beaker. Stir the water with a thermometer and measure its temperature after every half a minute interval. Record the readings in table 1. At exactly 2 minutes, add all of solid A to the water at once. Stir well and continue measuring the temperature of the mixture after every half a minute interval. Record the readings in table 1. Retain the mixture in the beaker for use in procedure 2. So, want to use these values. Let us use 24. You can put 0.0 to 1 decimal place. 24.0, 24.0, 24.0. The reason why I'm putting 24 because this is you are measuring the temperature of this water at room temperature before you have added anything. So the room temperature could be 24, 23 depending on the weather that day. So up to this, now when the time is exactly 2 minutes, you can see 2 minutes where there is X. You add all the solid A at once. So from that now, the temperature will start rising or decreasing, it depends. But for this one, the temperature was decreasing. And we want to use, the first one was 31. After half an hour, the temperature rose up to 31. At the third minute, the temperature went to 32, and then 33, stood at 33, stood at 33, and then dropped to 32. So this is the trend, increase and then decrease. There you have all the table is filled. I used 1 decimal point. Please ensure if you use a decimal point, one of them, make sure that you use the decimal point constantly or consistently. So now this is our table. Here you expect to have 3 marks. On the grid provided, plot a graph of temperature, vertical axis against time. When you are told to plot a graph of temperature against, so against, the one which comes after the word against is always the x-axis. Time. X-axis comes after against, the word against, and then the vertical. They have also told you vertical axis. That is the y-axis. So this is temperature. So make sure you are convenient. You know how to put the scale, because if you put the other way around, you will not get the mark for labeling. So let us go straight and look at the graph. Now let us draw a graph. You take your ruler, you draw the y-axis. Take your ruler, you draw the y-axis like that. Draw the x-axis. Draw the x-axis like this. After drawing that, label the x and the y-axis. We have been told to draw a graph of temperature, so we name here temperature temperature is always in degrees Celsius, and then against time. This time of ours is in minutes. So by doing that, you already have a mark, That's 1 mark for labeling. Now let us give it the scale. We will give here a 0. But remember, temperature, room temperature, we cannot have a temperature of 1, 2, 3 up to 10. So what we do, we can break this graph. We can break the graph so that we can have a reasonable temperature. So we can begin somewhere here at a temperature of, remember our range is 24 to 32. 24 to 32, therefore we can start here 23, right? And then 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, and 35. And 35. So we have now labeled the vertical scale which for temperature. Now let us go for time. Our time, we have a range of half an hour, half a minute. So from 0 we can have 1 minute at this point, and then 1.5, 2 minutes, 3 minutes, 4, and 5. So in between here 0 and this is a half. This one will be 1.5, 2.5, 3.5, 4.5, and we have finished with the scale. Now we have already scored 2 marks. That is for the scale labeling, like that, choosing a correct scale that covers at least 3/4 of the graph. The next thing is now to plot the graph. When time was 0, our temperature is 24. So you should always remember this information here. When temperature is 0, when time is 0, temperature is 24. When time is a half, 24. When time is 1, 24. When time is 1.5, 24. So that is what we are doing. So when time is 0, the temperature was 24. So we put that point there. Another point here. Another one here. Another one here. Up to that point. Because at 2, there is nothing we did. We didn't take the temperature when time was 2. So when the temperature, and then from here we have 31. So at the 2.5 we have 31. So we go, where is 31? 31 is here. You put a dot there or an X. At 3, that is 32. At 3.5 we have 33. At 4 we have 33. At 4.5 we have 33. And then at 5 we have 32. Now this is a straight line. You draw a straight line from this point. I hope you are conversant with the graphs dealing with energy changes. These are the graphs. We have endothermic graph, exothermic graph. Those are the things you need to understand before you go to an exam room. So I have plotted these 2 points. This means that after you have this point, you extrapolate this point to this side, extrapolate where the 2 points are going to meet. That will give us the maximum temperature reached. So we extrapolate. You use now a dotted line like this, and then this side, dotted line. Very good. Now we want to read our maximum. For us to read the maximum temperature, we use a dotted line towards the y-axis. Don't worry about this. So this is at this point. So our maximum is 34 degrees Celsius. That is the temperature. Remember, let us also join this one, our room temperature, this. Now we are measuring the temperature between the minimum, this is the minimum, and the maximum here. This temperature here and here. This is what we are measuring. So let us go to the question. Determine from the graph the temperature change. So we have done from the graph. So how will you show that you have used the graph? You must extend this line. You must extend this line. And then from this, where the two lines meet, you go across like this with the dotted line. That will show that you used your graph. That's how you will get this 1 mark. So ours is 34 minus our initial, which was 24. And that one will give us 10 degrees Celsius. And that is the temperature change. Calculate the number of moles of solid A used. So to get solid A, you go back to what you are provided. We are provided with 5.3 grams of solid A, sodium carbonate. So we have the mass and we have been given the RFM. So the mass of solid A, is 5.3 and the RFM is 106. But we know moles equal to mass over RFM, which is 5.3 divided by 106. And this one is the your calculator. That is 5. So it's off. 5.3 divided by 106. That one gives you 0.05. So we have 0.05 moles of the solid. Now question Roman 2. Calculate the molar enthalpy of solution and show the sign of the heat change. That is the enthalpy of solution. You show the sign. Assume that the solution density is this and the specific heat capacity is 4.2. Now here the first thing we calculate is the heat change. We know heat change equal to mass, capital M. This is the mass of the solution that was used. Remember we measured 30 centimeters cube of distilled water in which we added solid A and the temperature started rising. So the solution, the mass of the solution times the specific heat capacity times the temperature change will give us the heat change. Now this one we measured 30 centimeters cube of distilled water. Remember, you should know that the density equal to mass over volume. Now the density of water is 1. The mass we don't know, but we have the volume which is 30. So we multiply times 30 both sides. So X equal to 30 grams. Now this 30 centimeters cube is as good as 30 grams. Now we convert 30 grams to kilograms. So that is now 30 over 1,000. Now I've converted this to kilograms and times specific heat capacity, which is 4.2, times temperature change, which we calculated, which is 10. Now this one you take your calculator and it will give us 30 divided by 1,000 times 4.2 specific heat capacity and then times 10. So that one gives us 1.26. So 1.26 kilojoules. Right? Now the next one, now we want to calculate the molar heat of solution. So how do we know that this is the heat that was produced by 0.05 grams of the solid A? So we say that 0.05 moles of solid A was able to produce 1.26 kilojoules. We want to know 1 mole of A would produce what amount of heat, because we want mora enthalpy. Mora means for 1 mole. So 1 times 1.26 divided by 0.05. This one gives you bring your calculator, this answer, and then divide by 0.05. That gives you 25.2. Now this one is 25.2 kilojoules per mole. But remember, the reaction was exothermic. The temperature was rising, increasing. Therefore, our final answer should be negative 25.2 kilojoules per mole. That is the correct answer. Thank you. Let us go to procedure 2. Procedure 2. Fill a puree with solution B. You should always remember, what was solution B? Solution B is hydrochloric acid. Solution B is hydrochloric acid. These are the information which you must put at the back of your head, at the back of your mind as you continue to go ahead. So fill the puree. In the puree, we are going to have HCl solution B. Transfer all this mixture in the 100 plastic beaker from procedure 1 into a 250 ml volumetric flask. Add distilled water to make up to the mark and shake. Label the mixture solution A. Using a pipette and a pipette filler, place 25 centimeters cube of solution A into a 250 centimeters cube conical flask. Add 2 or 3 drops of phenolphthalein indicator and titrate with solution B. Do not pour out the content of the mixture of the conical flask. Don't pour. So you need to follow instructions. That's why you are supposed to use 15 minutes first to read through the instructions before you start doing the practical. And then record the table and then add 2 or 3 drops of methyl orange indicator to the content of the conical flask. Titrate the mixture with solution B and record the reading in this second titration table 3. Yeah, that is it. So the information I want you to understand is that we have 30 centimeters cube of sodium carbonate solution from procedure 1. We have put the solution into a 250 volumetric flask. We are adding water up to 250 centimeters cube. So we are going to prepare a solution of solution A, which is equal to 250 centimeters cube. Right? This is the information you need to understand. So HCl is going to react with a carbonate. It's going to react with a carbonate solution. So that is correct. So let us see what we are going to fill in the table. Let us use these values. 16.5. 16.5. Our initial is 0.0, 0.0, and then our arithmetic is 5.5. 16.5, 16.5. So average volume solution B used here. So now we have 2, so that is 16.5 plus 16.5 divided by 2, which will give you 16.5 centimeters cube. Table 2, you will give you the same value, 16.5, 16.5, 0.0, 0.0, and then 16.5, 16.5. Remember, this value doesn't matter. But if you know, if you can pick just this value n and use it appropriately, step by step, you are going to score a lot of marks, and you only miss some accurate mark, which is 1 mark. But I don't recommend that you don't do the practical, but I'm saying that this value here, the average, it doesn't have much. The thing is, do you know how to use that value, the average you decided to use, correctly, step by step, down the questions? The average here is going to be 16.5 plus 16.5 divided by 2, and we have 16.5 centimeters cube. So this is how the table was. So let us go to the next page and see the questions. Calculate the concentration in moles per liter of sodium carbonate solution A. Right? But what was solution A? Remember very well, solution A is a solution that was made by dissolving 5.3 grams sodium carbonate in water, right? To make a 250 centimeters cube. We have been given RFM. We know how to calculate the moles, isn't it? So we can say, now let us get the number of moles in 250. So moles, we know that moles equal to mass divided by RFM. RFM is 106, which will give us 0.05, right? This is the number of moles of sodium carbonate in 250 centimeters cube, because our solution was made in a 250 volumetric flask. Therefore, this is the number of moles in 250. So, concentration in moles per liter. We want the number of moles in 1 liter. So we will ask if 250 centimeters cube of solution A has 0.05. We will only ask what will be the number of moles in 1,000 centimeters cube of solution A. So it is 1,000 times this divided by this, which is going to give you 0.2 capital M, or 0.2 mole per dm cube, mole per liter, mole per liter, mole per liter. That's one way you can do it. I want to do it in a different way. Another person can say like this: we know that the 5.3 grams, these are the number of moles that are in 250 centimeters cube. So we say 5.3 grams is in 250 centimeters cube, isn't it? Yeah, remember from the procedure, there are some things which you need to put in your mind. We dissolved solid A in 30 centimeters cube from procedure 1. That solution, we put it into a volumetric flask. Then we add water to 250. So the number of moles, or the mass in 250 is 5.3 grams. The one we used, right? So we will ask if 5.3 grams is in 250. We will find out what will be the number of grams, or the mass in 1,000. It is this times C divided by this, which is going to give us 21.2 grams per liter. This is now the mass in grams per liter. But we know, how do you calculate molality? We know what is molality. Molality is the number of moles in 1 liter. Molality equal to mass in grams per liter divided by RFM. We have mass in grams per liter, which is 21.2 grams per liter. And then we have RFM, 106 divided by 106. And this one gives you 0.2 capital M. Capital M stands for molality. Capital M stands for moles in 1 liter. Thank you. So the essence of doing it like this, or to giving two alternative. That's why I'm doing this. I'm not doing it. I want you to get the understanding, to understand morality, to understand moles, how to calculate moles, to understand mole concept. That is my task. That is my endeavor. So calculate the number of moles of sodium carbonate in 25, solution A. Now we have the number of moles in 1 liter. We also have the now calculate the number of moles of sodium carbonate in 25 centimeters cube of solution A. But now we have the number of moles in 1 liter. That is, this is the number of moles of solution A in 1 liter. Then we ask what will be the number of moles in 25 centimeters cube of solution A. So we'll say 0.2 capital M means number of moles in 1000 centimeters cube of solution A. Then we ask 25 centimeters cube solution A will contain what moles? 25 times 0.2 divided by 1000, which will give you 0.0125 moles. Calculate the number of moles of hydrochloric acid in the total volume of V1 and V2. The total volume. Now remember V1 we used 16.5 and the V2 was 16.5. So the total volume, our total volume will be 16. So total volume would be 16.5 plus 16.5, which is equal to 33 centimeters cube. That's our total volume. Solution B. But we don't know the number of moles of solution B. There is no much information we have for solution B. Remember, solution B, the only thing we know about solution B is just that you are provided with solution B, hydrochloric acid. But since now it has reacted with the carbonate, we can get the number of moles there. So sodium carbonate will react with HCl, giving us sodium chloride plus CO2 plus water. But we will balance because these 2 here, we will put 2 here, we put another 2 here. So the ratio for the carbonate and HCl is 1 and 2. Right? But we know the number of moles of the carbonate from here, the number of the carbonate that reacted with this HCl, 33 of it. So if with this number of moles is 0.01, this one, to 5, then the number of moles of HCl will be twice because the ratio is 1 to 2. So moles of HCl in 33 centimeters cube that reacted with the carbonate equal to twice 2 times 0.1 0.0125 which is equal to 0.0 what is that? Let us use the calculator kindly. So answer times 2, which is equal to 0.025 moles. So this is the number of moles of HCl in 33 centimeters cube that we also used. Roman 4. Calculate the concentration in moles per liter of hydrochloric acid in solution B. Concentration in moles per liter. Concentration in moles per liter means number of moles in 1 liter. Molarity. It means molarity. But we know that the 33 centimeters cube of solution B has 0.025 moles. Then what will it be? 1000 contain. So 0.025 is the number of moles contained in 33 centimeters cube solution B. 1000 centimeters cube solution B will contain how many moles? 1000 times 0.025 divided by 33. That one is going to give us 0.7576 capital M. Capital M stands for moles in 1 liter, molarity. Now allow me take you through the qualitative part of it. You are provided, that's question 2, you are provided with solid C, carry out the following test, write the observations and inferences in the spaces provided. Place all solid C in a boiling tube, add about 20 centimeters cube of distilled water, and shake until all the solid dissolves. Label the solution as solution C. Use about 2 centimeters cube of solution C in a test tube for each of the following tests. A. Add aqueous sodium hydroxide dropwise until in excess. This is now where the students go wrong. When you are told to add dropwise until in excess, what it means, first, use 2 drops, make the observation, see what will happen, and then afterwards, add the sodium hydroxide in excess and then make another observation, because here you are expected to make 2 observations at once, simultaneously. So this is what was observed. White PPT. So this is the first observation. When you put a drop, a white PPT is formed. Then what happens when the white precipitate, when the sodium hydroxide, what happens to the white precipitate when sodium hydroxide is added in excess? The white precipitate is formed, which now make form for the excess, which dissolve, or which is insoluble, which does not dissolve in excess. In excess sodium hydroxide. So this is the expectation. Whenever you are asked to add sodium hydroxide dropwise and then in excess, then you should first use the 2 drops, make the observation, and then add in excess, make the observation. So a white PPT is formed which is insoluble, which does not dissolve in sodium hydroxide, meaning the white precipitate remains, persists. So if that is the case, then what is present? What is present is that calcium, 2 ions, magnesium, 2 ions, and barium, 2 positive, are present. If the white precipitate dissolve to form a colorless solution, then we know the amphoteric ions are there, aluminium, lead, and zinc. But since this one it is insoluble in excess, it means that the calcium ions, magnesium ions, and barium ions are present. Now you can ask me, is it correct for you to write that lead 2 positive, aluminium 3 positive, and zinc 2 positive absent? It is correct, but unacceptable. It is correct, but nowadays they don't accept that. If it is not there, then tell us what is there. That's why I've given you what is there. Now you know, whenever this happens, what is there is calcium, magnesium, and barium. If it happens otherwise, the white precipitate dissolve to form a colorless solution, write this and this and this present. Don't write this and this absent. Write what is there. Thank you. Add 3 drops of aqueous sodium sulfate. We are adding sodium sulfate. So you are seeing the sulfate. Here we expect, because remember all salts of sodium are soluble. So we are going to expect that this one, if it gets into that solution in our test tube and finds lead, 2 ions, it will form a white precipitate. If it finds barium, it will form a white precipitate. If it finds calcium, it will form a white precipitate. The sulfate. We know salts of sulfates which are insoluble, which forms white precipitate. So what was the observation for this one? White precipitate is formed. So if a white precipitate is formed, but from the if you put that lead is present, then you are contradicting yourself, because initially in our previous inference we said lead is not there. So you don't, where will you get it from so that you can put it here? Therefore, you don't add that because it was not there initially in the previous observation. Therefore, here it is only calcium and barium that are present. Calcium 2 ions or barium 2 present. Sorry, barium nitrate. Whenever we are adding barium nitrate, we expect a white precipitate, because barium will form barium sulfate, barium carbonate, barium sulfite. These are the three salts or anions that will form a white precipitate with barium. But now, since there is no white precipitate, then it means the sulfate, the sulfite, and the carbonate, they are absent. They are not there. Otherwise, if they were there, barium would form a white precipitate with n of them. Add 3 drops of aqueous lead 2 nitrate. Lead 2 nitrate. Heat the mixture. We have been asked to heat the mixture. Heat the mixture. Then this is the observation. A white precipitate, white PPT formed. The observation we have made is for adding red to nitrate. After heating, what happened? Did the white precipitate dissolve on heating or it did not? That is the second observation. A white precipitate is formed which dissolve on heating. So that tells you, if you are adding this, then it means a chloride was there. A chloride. So that it forms lead chloride. Lead chloride is the only salt which forms a white precipitate, and when warmed or heated, it dissolves to form a colorless solution. But is it only chloride? You can also use bromide ions. So bromide ions and the chloride ions will behave in a similar way, because actually they are halogens, you can see. So these two will behave like that. So you say this or this is present, and you get your marks, all of them like that. Let us go to the last bit of it. You are provided with an organic compound. Very important. You have been asked, you have been told, you are not going to find out whether it is an organic. This one you have been given straight that it is an organic compound. So did it carry out the following test, record the observations and inferences in the space provided. Describe the appearance of solid D. It was a white crystal, therefore you say white crystalline solid. Or you can say that's or white crystals. You can say it is white crystals because the salt was white. Divide solid D into 4 portions. Yes. Place the first portion of solid D on a watch glass and burn it with a Bunsen burner flame. Then what happened? Remember, it is a solid, so the solid melt and burns with a yellow sooty flame. The solid D melts and burns with a yellow soot flame. Now we want to know whether it is a saturated organic compound or unsaturated. If it burns like this with sooty yellow, then that tells you it is the unsaturated, the double bond or the triple bond. Present. It is acceptable for you to say unsaturated organic compound present. It is acceptable to say unsaturated organic compound present. It is acceptable. Place the second portion of solid D in a test tube. Add about 3 centimeters cube of aqueous sodium hydroxide. Now you see, here we are using aqueous sodium hydroxide. Basically, we want to test whether this organic compound is basic, is neutral, or is an acid. Because if it is an acid, it's going to produce effervescence. That's why we are using a base. We basically want to test whether it is an acid. Yes. So let me give you the observation. The solid dissolve, solid D dissolve in sodium hydroxide, then it dissolves in sodium hydroxide, forming a colorless solution. Now remember, a solid is dissolving in sodium hydroxide, which is a base. Then that one definitely tells you that this solid was acidic, right? Yeah, an acid plus a base, it will give you a colorless solution, neutralization reaction. But now we are dealing with organic chem. Here we give the inference of organic acids. It is acceptable for you to write that acidic organic compound present compound. Acidic, it is acceptable. But also, if you don't remember this, you can write that the functional group of alkanoic acids is present. It means that alkanoic acids are present. One of them is present. Number 3, place the third portion of solid D in a test tube. Add about 3 centimeters of distilled water. Heat the mixture and add 3 drops of acidified potassium manganate 7. Acidified potassium manganate 7. Then the observation is that this one is decolorized. So you just say acidified potassium manganate, permanganate, that is, solution is not decolorized. We have reviewed that it did not decolorize. So another person can say the purple acidified potassium permanganate remains purple because it did not change. We know this one is purple. So if it doesn't change, then it means that the double bond, the triple bond, or the alcohol ROH was absent. Yeah, is absent. If this were present, the acidified potassium manganate would be decolorized. It could change from purple to colorless. But now it did not. It didn't do that. Therefore, it means that these 3 are absent. they are absent. Finally, place the fourth portion of solid T in a test tube, add about 3 centimeters cube of distilled water, heat the mixture and add all the solid sodium hydrogen carbonate provided. Then effervescence occurs. That now confirms actually that solid was an acid. Effervescence occurs. Carbonate plus an acid, we always expect carbon dioxide to be produced, therefore effervescence will occur. That confirms that the alkanoic acid are present. Okay, H. The alkanoic acid are present. It is acceptable to write that acidic organic compound present. This is the last printed page. I want to thank you. Kindly do me a favor and subscribe. Also share to your friends, please.